All right. Good morning, everyone. Starting nice and prompt here right at 11:01 a.m. for our chat with IODP Expedition 395C, Crustal Objectives chat with our co-chief scientists. My name is Jose Cuevas. I am currently a graduate student at Boston College. I'm also the outreach officer for IODP Expedition 395C. Joining me today, we have Anne Briais from CNRS, Geosciences Ocean IUEM Brest, and we also have Ross Parnell-Turner from the Scripps Institution of Oceanography. They are the co-chief scientists of this very unique drilling expedition. So thanks to both of them for joining both very early in the morning and a little bit later in the afternoon than might usually be expected for a work call. And also thanks to all of you for joining across different time zones as well. That is one particularly unique thing about this expedition, where we're able to connect with different people from different time zones. But I think it's also something that has historically been a strength of IODP, because it does lean heavily on international partnerships. For example, Anne is in France, Ross is in the United States. I am in a completely different part of the United States. But good morning, everyone. Did you two want to introduce yourselves?
Sure, I can go first. Hi, I'm Ross Parnell-Turner. I'm a marine geophysicist at Scripps Institution of Oceanography, which is part of the University of California in San Diego. And as Jose said, I'm one of the co-chief scientists for Expedition 395C.
And I'm Anne Briais, and I'm at the CNRS in the lab called Geosciences Océan. So I'm a marine geophysicist as well, and I'm also a co-chief of the project 395, and which is now Expedition 395C. But we'll come back on the fact that it's both a unique and a multiple expedition project.
Right. Yeah. So thanks again for joining us. Like I said, it is later in the afternoon than expected for Anne, and earlier in the morning than expected for Ross. So thanks to both of them for donating their time and being willing to tell us about this unique expedition. So I feel like we should start with what IODP is, right? Like I started off with an acronym, which you shouldn't do. But IODP stands for International Ocean Discovery Program, and it's the newest version of a series of different broad projects about what's called scientific ocean drilling, right? So this started with something called Project Mohole, wherein scientists wanted to see if they could dig into the mantle of the Earth completely through the crust. Did that succeed? Do we know?
No, it was not successful in drilling through to the mantle, although they tried very hard. And actually drilling through to the mantle remains to be one of the major objectives of the current drilling program. But even though they didn't make it through to the mantle, they learned lots of clever things about how to go about doing scientific ocean drilling. There are a whole bunch of engineering feats that they managed. One of the most important probably was figuring out how to keep the ship in one place, to keep drilling in the same spot, which is a technique called dynamic positioning, which is really important when you're trying to drill a hole which is hundreds of meters below the seafloor.
Yeah, and if you've seen the 1970s King Kong with Jeff Bridges, dynamic positioning also played a part in that movie because they were able to use a research ship to keep some of the sea shots in the same place. Yeah. So from there, they were able to use those to improve drilling technologies. And into today, we have a new program called the International Ocean Discovery Program, which is about to embark into a new scientific framework moving into the year 2050. So I have a few of the points written down here. It says, we research the processes that connect the solid Earth, ocean, life, climate, and society. We explore the interconnected Earth in places that can only be accessed and understood through scientific ocean drilling. And we traverse time to reveal the many interactions that shaped Earth's geologic past to illuminate our future. We communicate knowledge gained through scientific ocean drilling to the global community. And I feel like the global community is a point that's kind of been part of IODP for a while now. It has international in the current title. And we have, whenever we are able to collect samples through scientific ocean drilling, we don't just like leave them wherever we found them. We store them in different places called core repositories, right?
Yeah,
what were those
again? Yeah. So there's been a lot of cores collected so far for many years now by the different programs, and so there are three main repositories. One in Japan, the CoChiefs repository. One in Europe, in Bremen, and one in Texas, in College Station, the Gulf Coast repository. And basically, the cores are distributed in between these three repositories in terms of geographic areas. So the cores that are collected now by just south of Iceland in the North Atlantic will end up at the end in Bremen in Europe, and all the Pacific cores are in Texas, and the Indian Ocean cores are in Japan, in Kochi.
So just to give everyone a really quick look at just how vast this program is, here's a map of the different sites that IODP has been able to collect cores and collect samples at. And this is not really complete. I think this is current as of 4 or 5 years ago. But you'll see that we've been able to sample almost the entire global ocean, which is why we need so many core repositories, first of all, and second of all, why they are in so many different places, to really highlight that international collaboration. This is really a global effort on behalf of all of the scientists, both aboard and ashore. So that's really cool and really interesting. So where is this current expedition?
Shall I take that one? So the current expedition.
So I think it's fine.
The current expedition, and when I say current, I mean the ship is there right now. They're actually drilling through basalt several hundred meters below the seafloor. Is located about a day's sail or a few hundred miles south west of Iceland, on a patch of the mid-Atlantic ridge called the Reykjanes Ridge. And they're going to be spending the next 60 days in this location. There's an excellent map. They're going to be spending the next 60 days at these locations marked by those little tiny orange dots you see there. And we're going to be drilling at 4 or maybe even 5 sites where we're going to be drilling down hundreds of meters below the seafloor.
Yeah, that's really cool. And I think we do have a slightly relevant question here. So Subsonic wants to know, when you drill down, how far back in time can you go?
That's a good question. Well, we can. I think the farthest we can drill is 8,000 meters altogether. So you can go down a lot of sediments. The limit is the stability of the hull most often. So that's why we often install structures to help consolidate the top of the hull. And in our case, we're going to install like 600 meters, like sort of metal cylinders to consolidate the top of the hull. And then it depends on the rate of sedimentation. And so it's going to be a factor that's going to be very important also in our case. In the North Atlantic, the sedimentation rates in some of the sites are very high, but in the case where the sedimentation rate is very low, then 100 meters or 1,000 meters a core can go very far back in time. So
So you mentioned the sedimentation rates. Are there any other ways that we can be sure of how old a particular core is?
Well, in our case, we can reach the basement, and so there are various ways to give an age to the ocean crust, and so we're going to have the ages from the small foraminifers, the small fossils in the sediments just above the basement. And then we're going to have cores of the basals. And so we're going to have the age of the basals in absolute ages. And also at the surface, Ross and the crews that prepared for this expedition collected magnetic anomalies. So the magnetic record of the basals is also visible from the surface. You just have a magnetometer just behind the ship, and you can also record the magnetic history of the ocean crust. So that's 3 ways we can date the basals.
And we already. Sorry, go for it.
No, just to mention the oldest site we are aiming for is 32 million years old. I mean, the crust there is 32 million years old, and we're hoping to reach the basals there, but probably not this year. Probably not with this expedition. Hopefully next year and or later.
Yeah.
Sorry.
No, you're good. And so it's 32 million years, and this is also a place in the ocean where new crust is being made, right? Kind of.
I just lost your connection there. Could you repeat that?
No, that's fine. This is a place in the ocean where new crust is being made, right? So the basalt here would be younger than it would be in other parts of the ocean?
Yeah, that's right. So in the middle of the oceans, new crust is being formed all the time, and so you can kind of think of the world's oceans as like a giant baseball with a seam that goes around it, and that seam is where the new crust is being formed, and it's brand new. So like every day, there's a new piece of crust being made. And as the tectonic plates spread apart, that crust gradually cools and moves away from that baseball ball seam, and it ages and it cools and it gradually sinks to deeper and deeper down. And then eventually it gets recycled back inside the interior of the Earth in places called subduction zones. And the oldest crust on Earth is around 250 million years old. So wherever we look on Earth, the surface of the oceans is actually relatively quite young because it's continuously recycled, being sent back down inside what we call Earth's mantle, and then comes back up again at the ridges.
That's cool, yeah. And then we do have a picture of some of the basalt that we have collected. This is new within the last week. So this is a brand new sample. This is something that we just drilled out.
Yeah.
Yeah, so this is really cool. This is the very first piece of basaltic crust that we've collected at one of our sites during this expedition. I think we recovered this piece of rock on Tuesday morning. It doesn't look all that exciting, I guess, in this photo, but the black thing you see in the middle of that photo is a piece of basalt, which is a couple of million years old. We're going to be using the chemical composition of that basalt to tell us about how the ocean crust was formed a couple of million years ago.
So there's a lot of geology in this expedition, as well as a lot of physics and chemistry, and not just by themselves. They're all working in tandem to tell us more about the story, not only of the North Atlantic, but of like how the mantle works in general.
Yeah, that's right. So we have a whole bunch of different scientific objectives, and one of the exciting things about these drilling expeditions is that it's not just a single scientific question we're trying to answer. We have a whole bunch of different things we're trying to do. So one of them involves looking at those basaltic samples that we just saw a photo of. And then we're also interested in not only how that basalt forms, but also how it gets weathered and altered as it ages. So kind of how it gets beaten up by seawater circulating through it, which we call hydrothermal alteration. And then we're also interested in how ocean circulation has changed and climate has changed in the past. And for that, we're going to be using the thick pile of sediments that Anne was mentioning a moment ago to look at the record of climate that's contained in those sediments.
Okay, so we're collecting harder rock like the salt, and we're also collecting things that might look a little more like sand and feel a little more like sand, and we're able to use like sand and mud, and we're able to use both of those to figure out circulation and physics and chemistry.
Yeah, actually, the top sediment has a lot of water in it. So we're going to collect, or they are on board, going to collect the interstitial water, because these give a lot of information on all the interactions between the seawater and the sediment, and the history of the sedimentation, and also it might give some information on the life within the sediment. And so they're going to try collecting water all the way through the sediment down to the sediment basement interface. And then the water actually, as the mud goes deeper and deeper, the rock, the sediment goes denser and denser, and there's less and less water and less porosity. And then of course with the basalts, the fractures in the basalts could still contain some water, but much less than the sediment, of course. And actually, what's exceptional in our different sites is that they have all been all the basalts have been created at the same spot on the plate boundary. So the site that's 32 million years old has been created when the mid-ocean ridge was active 32 million years ago, and then the basalts cooled and drifted away from the plate boundary, and all the sites, the 5 sites in the expedition are located. Correspond to the same spot on the plate boundary. So we have a history of the plate boundary at that place through time, and that's really one cool thing about this expedition. It was also one of the objectives of the previous expedition, or previous sort of expedition. just like for us, the interview of the co-chiefs of the previous expedition, where they installed casing for future cores throughout on a transect across the South Atlantic, and we hope to maybe compare some of their results with our results, but there's a lot of coring to do before we can do that.
And just briefly speaking about your past work, and Seth Frank wants to say that they've sailed with you a number of times in the past, and it's great to see some continuation of this great research.
All right, that's Seth. Yeah, I remember. Yeah. I've been lucky to sail previously in the South China Sea on 2 whole 2-month cruises and 1 short one, and actually I came back from one of the expedition on 367 with they made us a nice gift of giving us a piece of liner. So that's what goes in the that's the tube which collects the cores actually, and it's engraved with the expedition number. And that was in the South China Sea, and so I had one expedition 349 in 2014, and one in 2017. I was that, and then one short one in 2018. So and I'm so frustrated not to be on board right now. So yeah, it was a really exceptional experience at every expedition. It's really amazing the amount of work that's being choreographed by all the IODP system. It's really very, very impressive. And, right.
That's fair. Ross, did you have a quick sea story that you wanted to share, or did you have something else that you wanted to show on the screen?
I guess I was going to mention Anna and I have been talking, but we also should point out that we're not the only people involved in this project, and we have an amazing team of scientists who are involved in this project. And this map shows some of them, most of them, those whom I could get a headshot for. And so we have a science party of 27 scientists, and they're from 9 different countries, which you can see here. About 12 months ago, we were planning to all be sailing together on this expedition, doing exactly the same objectives. But due to the COVID-19 pandemic, we were unable to sail last summer. And then since then, we've been making preparations to sail again this summer. But again, due to COVID-19, mostly due to travel restrictions, we were unable to be on the ship this summer. And so all of us, you can see on this picture, bar one person, a special person, who I'm going to come back to in a second, are here at home, in our spare bedrooms, in our labs, back in our home. Students following along as they do some of our science objectives this summer. And the special person here is Leah LeVay, who's this lady in the upper left corner. She's our expedition project manager, who's based at Texas A&M University in the USA. And she's on the ship right now, leading the team of technicians and scientific staff, and they're currently carrying out all of the scientific objectives for us, and doing an amazing job, and spending a lot of time on Slack and email, keeping us up to date with everything that's going on. So this is really a huge team effort that at the moment is being made possible by the amazing people who are out there on the drill ship, the JOIDES Resolution, right now.
Really quick, core on deck. The techs are watching from the ship right now, but they had to run away because there's a core on deck.
Oh, yeah. That's nice.
So I guess we could give you a little operational update. So we're currently on the second site of our second hole of our expedition, which is the first site. And during the week, we've had a lot of waiting on weather, which means there's been a pretty big storm system coming through. So they haven't been able to operate the whole time. There was about a 24-hour period with no operations. But since then, we've made some great progress. And just today, we're making great progress through the basalt section of our second hole. And we're hoping to have that done in the next day or so.
Nice.
Yeah, so we're planning to core at least 130 meters of basalt, and it takes about the penetration rate in the basalts, if my memory is good, is about 4 meters per hour. So the cores don't come up very quickly when we're coring basalts. It's much quicker when we're coring sediment. Mm-hmm. And so every core. So now the coring actually half cores like 5 meters, or aiming to penetrate 5 meters, and then they collect the cores. And so it takes more than, or about an hour, or a little more than an hour. And then so the cores, so they come up and things like that. So they are actually shuffled out of the liner, and then they are measured before being split. They are measured. That's several measurements of of the density and the magnetic susceptibility of the rocks. And then there are photographs that they're photographed, and actually the basement cores are they're taking 360 degrees photos, so that we have the photo of the core all around, and then the core is split, and one half is an archive, and it's not touched anymore. It's photographs also. Yeah, that's what it looks like, the half. And then the other one can be sampled. But during this expedition, because there's no scientist to help with the measurements, we've selected essential samples to take and essential measurements to be made on the course, so it's manageable with the team of there are about 15 techs on board during trying to do both the usual work and the work that normally scientists would do. So what we see here is so on the edge it's centimeters, it's not inches. It's a basalt with all the small dots are vesicles, and the vesicles are sometimes filled with some sediment. So some scientists will be interested only in what's inside the vesicles to try and study the interaction between the rock and the seawater. And some others would be interested only in the matrix to analyze where the mantle comes from that created the melt that created the basalt, and how much melt was produced, and what's the temperatures that were reached, and then the history of the melt as it went through the ocean crust to the bottom of the ocean.
So there are a lot of different specialists on the science party who are all working together and communicating to figure out exactly what the story is behind the basalt cores and the sediment cores.
That's exactly right. So, for example, we have a team of petrologists who are experts in looking at studying rocks just like these. Right now, they're scattered everywhere from literally Hawaii to the UK to China. And typically what happens in our current mode of operation is the shipboard technicians do an amazing job of preparing the cores, as Anne was describing, and then they photograph them. And then they usually, within several hours, they send photographs like the one we were just looking at back to us in our homes. And then the petrology team, who are these specialists, they'll help us make decisions about, for example, where to take a sample and where to run analyses of the basalts using some of the instrumentation on the ship. And I guess I should point out that the ship is not just a drilling ship. You can think of it as like a giant floating laboratory. And so it includes all kinds of high-tech equipment that you might expect to see in any research institution. And so, for example, for these basalt cores, we're really interested in knowing all the concentrations of different chemical elements in that basalt core. It's going to tell us how hot the basalt was, for example, when it was formed. And so they have a thing called a mass spectrometer on the ship, which can tell us the concentrations of the elements in that basalt core. And so the shipboard staff can take a sample from that core and then run it through the mass spectrometer in near real time, just several days after it comes onto the ship. And then we can start to understand how those basalts were formed.
It's fantastic. Yeah. So I feel like the looming question everyone's kind of had, and we've kind of talked about this a couple of times during the broadcast already, but like, how is it different not being on the ship while all of this is happening? because I know, at least for me, I have all of my regular summer research that I have to do, in addition to the duties I would have normally been doing on the ship. And I'm certain that for the both of you as tenure track professors, you also have a very large load of summer research to be doing, on top of coordinating a full research expedition while not physically there.
Right. Well, we've devoted some time during these 2 months just to follow all the operations, and so we planned a little bit ahead, and but of course we have to be very flexible with our time. For example, there's been 24 hours of waiting on weather, as we say, where there was nothing new happening. And now there's basalt cores coming up, so we might have to take decisions. We had a lot of meetings to prepare for, like, first various options of the cruise, of the expedition, and then we had tons of meetings to select which operations could be done without the scientists, and with what are the priorities, and whom to contact if there's a burning question about petrology or paleontology and everything. So we've tried to think about a lot of things in advance to anticipate most of the situations. But we're still interacting with Leah. So I'm lucky that the ship is only 2 hours time zone away from France, and but Ross is in California. So between the two of us, it's 9 hours jet lag, 7 hours with the ship, and so we get used to having Ross get up extremely early for meetings, and me getting late meetings. But yeah, we try. It's, I don't know if it's more frustrating for me or for Ross not to be on board. I have the advantage of maybe being able to imagine the times, and I mean what happens at which time, and what's feasible on board, and what they mean in terms of like running the measurements on the whole round corals or in split, and so I have all the images from the previous expeditions in here, but we hope to be all on board at some point to look at the cores and touch.
So it really sounds like that teamwork is coming into play, and working very closely with the staff who are aboard to make sure that everything can still happen.
Yeah, and actually, so Leah is the key to transfer all the weird demands from the requests from the scientists to the tech team, and the operations superintendent and the captain and everybody. I mean, she's the link to everything. Thank you, Leah.
Yeah, she's been super communicative, and I'm very thankful that she's there with us. Rather, she's out there with a shipboard party. So Ross wanted to share a picture.
Oh yeah, so I wanted to just kind of touch on one of the kind of amazing features of our planet that is one of the main driving forces for why we were interested in going to this very rough piece of the ocean in the middle of the summer south of Iceland. And that one of the most amazing things in this area are these ridges that you can see on the ocean floor south of Iceland, and they're called the V-shaped ridges. I'm not sure you can see I think you can see my pointer.
Yes,
so
we can.
here's Iceland right here, which hopefully some of you are familiar with, which is where that big eruption is happening over the last couple of months. And here's Greenland, just to get your eye in. And then the mid-Atlantic ridge, which is where the two tectonic plates are spreading apart, is down here where my mouse is pointing. And then unusually, you can just see, and this is just a Google Earth image, there's nothing special about this image I'm showing you. You can see these V-shaped ridges either side of the mid-Atlantic ridge. And these ridges have kind of caused scientists to scratch their heads really since they were discovered in the 1970s. And there was a guy called Peter Voigt, who was working for the US Navy Research Lab, who first kind of studied these V-shaped ridges and tried to figure out why they're there. And so one of our three main objectives for this scientific expedition is to try and unravel why we get these ridges and troughs south of Iceland. And to do that, we're going to look at that's why we're drilling the basalt and looking at the chemical composition of the V-shaped ridges and troughs.
It's fascinating.
And I was going to say, some of you might be more familiar with the V-shaped ridges and troughs than you think, because there's a famous film called The Hunt for Red October, where there's a haywire Russian submarine captain who's driving his submarine around the North Atlantic, starring Sean Connery. And he used those, in the story, he used the V-shaped troughs, these bathymetric lows in the ocean, to hide his submarine away from detection. And so it was true that during the Cold War, the V-shaped ridges were used to conceal submarines as they snuck around in the North Atlantic. So you may not know it. You might have already kind of seen a V-shaped ridge in the movies.
So we're also trying to figure out exactly how those are formed based on different things happening with the mantle.
That's right. So we've got we've got a bunch of different hypotheses or ideas about how those V-shaped ridges are formed, and there are really three main hypotheses that we're trying to test. Like any good science experiment, like the kind of thing you might do in a high school science fair, we've got three hypotheses, and we're going to test them by making some observations. So whether you're doing science on a bench top in a high school, or whether you're doing science with this giant research ship, the principle is the same. And so we have three different hypotheses for how these ridges are formed. And maybe I can show you one of them is that, actually, can I just go to a different picture here?
Yeah.
Yeah, we'll stick with that one. So one of them is that we have blobs of hot material that comes up underneath Iceland through what's called the Iceland mantle plume. And on this diagram, which maybe is a little bit complicated, but this black arrow shows what's meant to be the underneath Iceland. So hot material is coming up underneath Iceland. It spreads out underneath the tectonic plate, which is this gray block here. And then every now and again, we get blobs of anomalously hotter mantle material, which is shown by these red blobs. And they cause slightly thickened crust to be formed on the mid-Atlantic ridge, which is this black line here. And every time we get a hot blob of material, we generate slightly thickened crust. And that results in this pattern of thick and thin crust shown by this satellite gravity anomaly map. So this shows those V-shaped ridges kind of in map view, the same way that I was showing them on Google Earth. And if I skip down here, so that was hypothesis one, and maybe I'll let Anne talk about the two other alternative hypotheses.
Right. Yeah. Because the ridges are formed by a thicker crust compared to the troughs, but what could also travel down the ridge from Iceland towards the south are small discontinuities of the mid-Atlantic ridge, which are known also elsewhere on the mid-Atlantic ridge and other mid-ocean ridges to generate areas of thinner crust. And so they're called propagators when they move along the ridge axis. And so this is another hypothesis to generate these variations in crustal thickness along the ridge. It's just that it would be propagators involving less of a variation within the hotspot itself, but just variations more locally beneath the mid-Atlantic ridge, going down towards the south. And then the third hypothesis is kind of a mix with assuming that the variations in water content in the mantle generates melting anomalies where there's more water content in the mantle, and these melting anomalies also go migrate down along the Mid-Atlantic Ridge and would generate V-shaped ridges. So all these hypotheses imply various chemical content of the basalts at the ridge axis and along the V shapes or the V-shaped ridge or the troughs, or even in a site where there is no V shape. These all the contents, the chemical contents of the basalts will allow us to test which of these hypotheses are valid, is valid, and maybe none of them. Maybe it's a mix of a little bit of everything, and so that's why we have to drill, and so the four sites closer to the plate boundary are located on the troughs. The blue ones are on the troughs, and the red ones are ridges. So we have four sites located on V-shaped ridges and troughs, and then the fifth site located on the 32 million year old crust, which is kind of located on an area of higher crustal thickness, but which is not migrating along the ridge. So that will be that will allow to test these hypotheses, knowing that all these sites are located at the same distance. So the basalts at these sites have been generated at the same distance from the hotspot. So so that's the first objective of the expedition is to understand what generates the ridges and troughs, and more generally all the interaction between the hotspot, the Iceland hotspot, and the mid-ocean ridge.
So there's a lot of, it sounds like there's a lot of pretty complex geochemistry and geophysics in play, but just like Ross said, it comes down to the same principles as a middle grade science fair. We have three hypotheses or three educated guesses, and then based on what observations we're able to make, we can see which of those are true and to which extent they may be true, right?
That's right. And as Anne said, like any science experiment, we might find that all three of our hypotheses are not on their own correct, and that maybe there's some combination of them that best explains the findings.
Yeah, that's really cool. That professional science really is the same as it is kind of growing up and throughout one's education. It's honestly really inspiring. Okay, that one.
So I wanted to mention the other one of the other objectives we have, which is completely different to what we've just been talking about, although is strangely actually connected through the mantle. So this is a map that shows the North Atlantic Ocean, which we've been talking about for a while now. So again, Iceland is up here. And these little dotted lines are the routes that deep water flows through the North Atlantic Ocean. So cold, deep, nutrient-rich water is formed in the Norwegian Sea, which is off to the upper right here. And then it flows down southwards over this thing called the Iceland-Faroe Ridge right here, and also over this feature here called the Denmark Strait. These are two what we call oceanic gateways. They're kind of like giant natural lock gates of the oceans. And that cold, deep water flows down into the North Atlantic Ocean and follows this kind of tortuous path down past the Reykjanes Ridge, around this fracture zone that's down here, back up into this northern part of the Iceland Basin, and then off down here where it hugs the coast of Greenland and round into the main ocean circulation system. And this deep water flow controls part of the global ocean conveyor system. So it has implications for ocean circulation everywhere. And this map I'm showing you now is a snapshot of what we think happens today. But what we think might have happened in the past is that these two oceanic gateways, the Denmark Strait and the Iceland-Faroe Ridge, may have gone up and down over geologic time, over millions of years, due to the mantle plume underneath Iceland being either hotter or colder. So when the Iceland plume is really hot, it puffs up the whole of the North Atlantic region, causing those oceanic gateways to shut. And when the Iceland plume is relatively cool, the whole area is able to sink down a little bit. So those two lock gates are open and the water can flow over those two oceanic gateways. So why is that interesting for our drilling project? Well, our drilling sites are down here on this flank of the Reykjanes Ridge, kind of where my pointer is. And we can measure the rate at which the sediments are deposited through time using those little fossils that Anne was telling us about earlier on. And we can see whether the currents were stronger or weaker in the past and when they were stronger or weaker. And we can try and see if that connects or relates to times when we know the Iceland mantle plume was either hotter or colder. And so we're testing out this, again, hypothesis that deep water ocean circulation, which is something that affects everything from the climate to the conditions of ecosystems in the ocean, whether that's connected to processes going on deep inside the mantle plume underneath Iceland, which originates possibly all the way from down in Earth's core mantle boundary.
So this is where the mud and the sand that we're collecting as well come into play, because the fossils of the really small organisms, really the kind of plankton, but not really plankton in that mud, are going to tell us whether the Iceland plume was hotter or colder and what impact that has on how currents move, not only through the North Atlantic, but after the North Atlantic through the entire world ocean.
That's right. So, for example, that's one of the little fossils we use are called benthic foraminifera. And benthic means they like to live on the seafloor. Mm-hmm. And foraminifera is just the type of fossil they are. They're these little tiny little fossils. And you can imagine they're living on the seafloor, minding their own business, but they're bathing in that deep water that I showed you in that map. They're living in that deep water. And so when they're making their shells, the composition of their shells contains the signature of that deep water that they've been bathing in as they grow. And so if we can collect those shells from the sediment, we can analyze their chemical content. And when I say chemical content, I mean things like their carbon isotopes. Mm-hmm. We can understand what the deep water composition was like through time.
It's really cool. Yeah. All right. So it looks like we are coming up right on an hour here. So I want to thank both of you for giving your time. I know you're both very busy and you're both on 2 drastically different time zones. So Ross, I hope you have a great rest of your day, and I hope you have a lovely evening. Is there anything you wanted to say before we really wrapped up?
No. Well, I want to wish good luck to the expedition, to the current expedition, and hope the weather will be nice. And that's actually what if when looking at your map with all the sites of drilling, like one main problem with with the drilling ship is that it can compensate part of the heave related to the waves, but not it cannot drill, it cannot operate at very rough seas. So yeah, so hopefully the weather will be fine, and good luck to the expedition, and keep posted for the other results.
Yeah, I certainly hope so too. Fair winds and following seas are exactly what we want. So it's kind of a big ask for the North Atlantic, but we can definitely hope.
I just wanted to say thank you to everyone who's been listening. We appreciate you hearing about what we're up to. And I wanted to also say a huge thank you again to the technical staff and the crew and everyone else who's out there, from the people who are the captain of the ship right the way down to the person who's making breakfast every morning and keeping everyone's laundry clean. They're all doing an amazing job, having had to suffer through this global pandemic and go through extra protocols like quarantines and lengthy travel. And then also I wanted to give a big thank you to our funders, the funding agency, in particular the National Science Foundation, who provide most of the funding for this program, and also to all the other member countries who we also really important ways to keeping this program going and doing amazing science.
Yeah, genuine thank you to all of the individuals who make this possible. And if you would like to keep following along as the expedition continues, you can follow along on Twitter and Instagram, among other social media channels. Those are the 2 that we're kind of focusing on. So on Twitter, we are at the JR. On Instagram, we are at Joides_resolution. And you can also follow along with the hashtag Expedition EXP 395C on both of those platforms. I'm doing a fair amount of that from shore, but also one of the technicians, Sarah, is giving you a snapshot of day-to-day life and day-to-day science out in the North Atlantic as well. So you get to see both what the scientists on shore are doing as well as what the scientists are doing out at sea. So a huge thanks to everyone. Thanks again to Anne and Ross for hopping on this Thursday evening or morning. And we hope to see all of you soon. Bye.
Thank you. Bye-bye.